timing is everything. When I was in graduate school in the mid-1990s looking for a project to work on for my PhD thesis, amazingly enough, the first reports of planets orbiting sun-like stars were coming around at that time. And my thesis advisor suggested that I work on exoplanets.
MIT professor of astrophysics, Sarah Seeger, arrived in the field after the paradigm had already shifted. To her, the question was no longer simply, are there exoplanets out there? It was, could there be one like Earth?
When I want to think, I come here to the Great Lake, and I look out on the water and I just think about how wonderful life is, how fragile life is. It gives me hope that there's another planet out there where life could really thrive.
But what makes our world so special? What physical characteristics define our planet?
We're looking for a planet that has a solid surface, a predominantly rocky planet, but we're not expecting another planet to be exactly like Earth. When we talk about the planets we want to find, it's one that would be able to host life.
Even in the most extreme environments, like here amidst the glaciers and volcanoes of Iceland, the conditions that make organic life possible on Earth can be found if you know where to look.
La vie a besoin d'eau. Alors cela dit, de l'eau, on pense qu'il y en a presque partout dans l'univers. Mais essentiellement, en fait, si on regarde sous forme de glace. Et c'est pas ça qu'il faut. La vie telle qu'on peut l'imaginer, chimiquement, et surtout telle qu'on pourra la reconnaître, ce qu'il faut vraiment, c'est de l'eau liquide. Et ça, c'est pas évident, parce qu'il faut les bonnes conditions de température, de pression.
Based on everything we know of life on Earth, scientists like François Forget believe that for an exoplanet to host liquid water, like Earth, it needs to lie within a certain distance from its star, a region called the habitable zone.
D'ailleurs, on calcule que si on déplaçait, avec nos modèles, si on déplaçait la Terre de quelques pourcents vers le Soleil, en fait, le climat s'emballerait parce qu'il y aurait un peu plus d'énergie solaire, les océans seraient plus chauds, plus de vapeur d'eau, plus d'effet de serre, et hop, très vite, on peut basculer complètement, les océans peuvent totalement bouillir et s'évaporer. Et inversement, avec la Terre telle qu'on la connaît actuellement, si on la déplace de quelques pourcents vers l'extérieur, on l'éloigne du Soleil, eh bien il va faire plus froid, il y aura plus de neige, plus de glace, et cette neige réfléchit au rayonnement du Soleil, ce qui fait qu'il fait de plus en plus froid, et ça s'emballe inversement, et la Terre peut être complètement couverte de glace, ce qu'on appelle une Terre boule de neige. Ce qui fait que la Terre est particulièrement propice à la vie, c'est pas seulement qu'elle est couverte d'eau liquide, d'océans aujourd'hui, mais surtout qu'elle a été pendant toute son existence, pendant 4 milliards d'années, ce qui a permis à la vie de naître et d'évoluer.
The first mathematical model of planet habitability, produced in 1979, placed extremely narrow limits on the habitable zone. But recent advances in geological science have broadened the horizon.
Other than being at approximately the right distance from the sun, the main thing that keeps Earth habitable is the carbon cycle.
Penn State professor of geoscience, Jim Casting, is a world leader in the study of planet habitability and the vital role played by carbon. On Earth, carbon in the form of CO2 traps the sun's heat in our atmosphere. Without it, temperatures would plummet to below what life needs to survive. But CO2 doesn't just stay in the atmosphere.
the trees around us are photosynthesizing, and they're actually exchanging every CO2 molecule in the atmosphere every 10 or 12 years. But on long time scales, it's what we call the carbonate-silicate cycle, where CO2 in the combined atmosphere-ocean system is exchanging with carbonate rocks.
CO2-rich sediment washes into the ocean and is drawn into the Earth's crust at underwater fault lines, where a final geological mechanism completes the cycle.
To have a habitable planet like the Earth, you really need a long-term carbon cycle, and that has to be driven by some process like plate tectonics on the Earth that keeps the carbon moving around.
When our planet enters an ice age, this tectonic feedback restores a habitable climate. As oceans freeze, the uptake side of the carbon cycle slows, while volcanic activity continues, pumping CO2 and heat back into the atmosphere.
When you put in the feedback, you find out that the habitable zone, instead of being very narrow, is actually quite wide, and wide enough that there's a good chance that planets around other stars, at least one or more of them, could be within the habitable zone.
Casting's research had a momentous impact. By expanding the boundaries of the habitable zone, the carbon feedback loop vastly improved the odds of finding an Earth-like exoplanet where life might be possible. But the fundamental challenge of identifying an Earth-like planet remained. They're tiny, and therefore much harder to detect, compared to the gas giants that our instruments had observed so far. To see these Earth-sized worlds, a giant leap forward in technology was required.
I was a graduate student when the very first planet was discovered. In fact, I was at the conference where Michel Mayor made that announcement.
NASA astrophysicist Natalie Batalha graduated with a dream.
I would say my biggest hope was that we find an Earth-sized planet orbiting a star very much like our own sun, in a similar orbit where the conditions for life might be just right.
Five, 4, 3, 2, engine start, 1, 0, and liftoff of the Delta II rocket with Kepler on a search for planets in some way like our own.
In 2009, scientists launched a formidable new weapon in the hunt for life beyond our solar system. The first dedicated planet-hunting telescope, Kepler. At the time, it was the world's largest digital camera, using an array of 95 megapixel sensors to detect the infinitesimal dimming of starlight caused by transiting planets. So powerful that if turned towards Earth, it could detect a single porch light turning off. More importantly, it was the first instrument capable of detecting rocky, Earth-sized planets.
The first 2 decades of exoplanets was kind of like postage stamp collecting. Kepler really changed that.
Kepler monitored a select region of our galaxy over a 4-year period by taking a snapshot every 30 minutes, like an epic time-lapse photograph.
And from that data, we identified over 4,000 periodic transit events that look like viable planets. And in fact, we have confirmed through other follow-up observations that over half of them are indeed bona fide planets.
Kepler delivered not only the first rocky exoplanets, it revealed brand new kinds of rocky planets, like Kepler 10b. our first encounter with what scientists would christen lava worlds.
These are rocky worlds, same kind of density as Earth, but they're orbiting so close to their star that the surface temperatures are in excess of that required to melt not just rock, but iron. So you've got an entire hemisphere, something the size of the Pacific Ocean, even larger, that is an ocean, but it's not an ocean of water, it's an ocean of molten rock.
Kepler was the first celestial census. Extrapolating the data from the surveyed region, it gave astronomers a catalogue of the exoplanet population.
We've learned, I think, 3 important things. First, we've learned that every star that you see when you look up into the sky at night has at least one planet. The other thing that we have learned is that nature makes small planets more efficiently than large planets. The third thing we've learned has to do with the fraction of stars that harbor Earth-size, potentially habitable planets. And we can make the bias corrections to determine that number. And what we find is that it's about 22 to 25%.
At least one planet for every star in the sky. And as many as a quarter of them Earth-sized and orbiting within the habitable zone. Kepler revolutionized the way we see the stars.
Kepler was the pioneer. Kepler looked for planets transiting sun-like stars. And Kepler looked at a very distant field of stars for 4 years to try to find a planet like Earth that has a 1-year orbit.
Inspired by the success of Kepler, in 2013, NASA joined forces with MIT Lincoln Labs to develop an instrument that could deliver a more detailed survey of nearby Earth-like worlds.
The entire field of exoplanets is funneling towards the search for another Earth, a rocky world orbiting a small star, preferably in the habitable zone of that star.
As the project advanced, MIT professor Sarah Seeger was named Deputy Science Director of the Transiting Exoplanet Survey Satellite, aka TESS.
TESS wants to find stars that are closer, right in our neighborhood, actually. The camera has a lens assembly of 7 lens elements that refracts starlight onto a detector. And together, they make a giant strip. When you think of the sky as a sphere, from the bottom of one hemisphere all the way up to the pole. After 1 year of doing that, TESS will flip to the next hemisphere, and it will then do the same thing. And so over 2 years, TESS aims to study the entire sky.
By scanning nearby star systems, TESS aims to identify 50 Earth-sized exoplanet candidates for further investigation.